Hey there, science fans! Welcome to the exciting world of chemical kinetics. Ever wondered why some reactions happen in a flash, while others take their sweet time? That's what we're here to explore. Chemical kinetics is like the speedometer of chemistry. It helps us understand how fast reactions occur and what factors can speed them up or slow them down. This field is crucial in many areas, from designing new drugs to understanding how the ozone layer protects us. So, buckle up as we dive into the fascinating realm of reaction rates. Ready to explore the different speeds at which reactions occur? Let's go! Not all reactions are created equal when it comes to speed. Some reactions happen in the blink of an eye, while others take years, decades, or even centuries to complete. The speed at which a reaction occurs can tell us a lot about the nature of the substances involved and the conditions under which the reaction takes place. Some are lightning fast, like the explosion of fireworks. These reactions are so quick that they seem almost instantaneous, creating a burst of light and color that dazzles the eye. Others are incredibly slow, like the rusting of iron. This process can take months or even years, as the metal gradually reacts with oxygen and moisture in the air to form a flaky reddish-brown coating. And then we have those in between, like the burning of a candle. This reaction is neither too fast nor too slow, providing a steady source of light and heat over a period of hours. We categorize reactions into three main types based on their rates: fast, slow, and moderately slow. Understanding these categories helps scientists predict how substances will behave under different conditions. Fast reactions. These are like the cheetahs of the chemical world, happening almost instantaneously. They are often dramatic and can release a lot of energy in a very short time. Think of ionic reactions, where charged particles zip around and react in a snap. These reactions are crucial in many industrial processes and biological functions. Slow reactions. These reactions are more like snails, taking their time to reach completion. They often involve complex changes at the molecular level and can be influenced by factors like temperature and pressure. The formation of coal from dead plants over millions of years is a classic example. This slow transformation involves the gradual accumulation and compression of organic material, eventually turning it into a valuable energy resource. Moderately slow reactions. As you might guess, these fall somewhere in between. They are not as rapid as fast reactions, but are quicker than slow ones, often taking minutes to hours to complete. The digestion of food in our bodies is a good example of a moderately slow reaction. Enzymes break down the food into nutrients that our bodies can absorb, a process that takes several hours. Now that we know how to categorize reactions based on their speed, let's learn how to measure it. Scientists use various techniques to determine reaction rates, such as monitoring changes in concentration, temperature, or pressure over time. Understanding these rates is crucial for developing new materials, medicines, and technologies. Just like we use a speedometer to measure the speed of a car, we use something called the rate of reaction to measure how fast a reaction is going. It tells us how much the concentration of reactants decreases or how much product is formed over a specific time. Imagine baking a cake. The rate of reaction would tell you how quickly the batter disappears and how fast the delicious cake forms. But how do we actually measure this rate? Stay tuned to find out. Chemists have a whole toolbox of methods to measure reaction rates. These tools are essential for understanding how fast or slow a chemical reaction occurs, which can be crucial in both research and industrial applications. Here are a few favorites that chemists rely on to get accurate measurements and insights into their reactions. pH measurement. Ever used litmus paper? It's a simple yet powerful tool. Changes in pH can indicate how fast a reaction involving acids and bases is progressing. For more precise measurements, chemists use pH meters, which provide digital readings of the acidity or alkalinity of a solution. Change in optical activity. Some molecules rotate polarized light. This property is particularly useful in studying reactions involving chiral molecules, which are molecules that have non-superimposable mirror images. By tracking changes in this rotation, we can monitor reactions involving these chiral molecules. This helps in understanding the stereochemistry of the reaction and the formation of specific enantiomers. Change in pressure. For reactions involving gases, pressure changes can be a telltale sign of reaction progress. Monitoring pressure helps in understanding the behavior of gases under different conditions and can be crucial in industrial processes. Change in conductance. Solutions with ions can conduct electricity. This property is used to measure the ionic strength of a solution, which can change as a reaction proceeds. By measuring changes in conductance, we can track reactions involving these charged particles. This is particularly useful in electrochemistry and reactions involving electrolytes. Now that we know how to measure reaction rates, let's explore the factors that can affect them. Temperature, concentration, surface area, and catalysts are just a few of the variables that can influence how quickly or slowly a reaction occurs. Get ready for some exciting chemistry. Understanding these tools and factors not only helps in academic research, but also in practical applications like pharmaceuticals, environmental science, and materials engineering. Section 5. Factors affecting reaction rates. What makes reactions zoom? Just like the weather can affect how fast a car can go, several factors can influence reaction rates. Imagine driving through a storm versus a sunny day. The conditions around you make a huge difference. Similarly, in chemistry, the environment and conditions surrounding the reactants play a crucial role in determining how quickly a reaction proceeds. First, let's talk about the nature and concentration of reactants. The type of chemicals involved can significantly impact the speed of the reaction. Some reactants are naturally more reactive than others. For instance, sodium reacts explosively with water, while iron rusts slowly over time. Higher concentrations of reactants usually lead to faster reactions, kinda like adding more fuel to a fire. When you have more molecules of the reactants, they collide more frequently, leading to a quicker reaction. Next, temperature. Heat things up, and reactions generally speed up. This is because higher temperatures provide the energy needed for molecules to move faster and collide more often. Think of how food cooks faster at higher temperatures. The same principle applies to chemical reactions. The added heat accelerates the process. Then, there's the surface area of reactants. The more surface area available, the more opportunities for reactants to come into contact with each other. Breaking a reactant into smaller pieces increases its surface area, allowing more contact between reactants and speeding up the reaction. Imagine trying to dissolve a sugar cube versus granulated sugar. The granulated sugar dissolves much faster. We also have radiations and catalysts. These can significantly alter the speed of a reaction. Certain radiations and catalysts can act like shortcuts, providing alternative reaction pathways that require less energy and speed up the reaction. Catalysts are like a secret ingredient that makes everything happen faster without being consumed in the process. And finally, the pressure of gas. This is particularly important for reactions involving gases. For reactions involving gases, increasing the pressure is like squeezing the gas molecules closer, leading to more collisions and a faster reaction. Higher pressure means the gas molecules are packed tightly, making it easier for them to interact. Understanding these factors is key to controlling reaction rates in various applications, from industrial processes to biological systems. Whether you're manufacturing chemicals on a large scale or studying metabolic reactions in the human body, knowing how to manipulate these factors can make all the difference. Section 6. Rate laws, unlocking the secrets of reaction speed. Rate laws are mathematical expressions that reveal the relationship between the rate of a reaction and the concentrations of the reactants. They are like secret codes that unlock valuable information about reaction speeds. The rate law for a reaction is determined experimentally and tells us how much the rate is affected by changes in the concentrations of each reactant. It's like a recipe that tells us the precise amounts of each ingredient needed for the desired reaction speed. By understanding rate laws, we can predict how fast a reaction will proceed under specific conditions, which is essential for optimizing chemical processes. Section 7. Pseudo-first-order reactions, sneaky reactions in disguise. Sometimes reactions like to play tricks on us. Pseudo-first-order reactions seem like they should follow one order of reaction, but they actually follow another. Sneaky, right? Imagine a reaction with two reactants, but one is present in a much larger amount than the other. The reaction rate might appear to depend only on the concentration of the less abundant reactant, making it seem like a first-order reaction. But don't be fooled. It's just the more abundant reactant masking its influence because its concentration remains relatively constant throughout the reaction. These reactions highlight that we need to consider all factors carefully when determining reaction orders. Section 8. The Arrhenius equation: temperature's role in reaction time. We've already seen how temperature can speed up reactions, but the Arrhenius equation gives us a precise mathematical relationship between temperature and the rate constant of a reaction. This equation is like a magic formula that helps us calculate how much faster or slower a reaction will proceed at different temperatures. It's like knowing the exact temperature setting on an oven to bake the perfect cake. This equation is incredibly useful in various fields, from designing experiments to understanding the effects of climate change on chemical reactions in the environment. Section 9. Photochemical reactions. Light up the reaction. Some reactions get energized by light. Photochemical reactions, like photosynthesis in plants, use light energy to kickstart chemical transformations. The rate of these reactions depends on the intensity and wavelength of light used. It's like adjusting the brightness and color of a lamp to influence the growth of a plant. Understanding photochemical reactions is crucial for developing sustainable energy sources, creating new materials, and unraveling the secrets of light-driven processes in nature.